Hello, today we're going to talk about nuclear equations. We're going to do so looking at some examples of radioactive decay. Radioactive decay, if you recall, is a spontaneous process that occurs to radioactive substances. So the substance undergoing the decay, what we're starting off with, is known as the parent isotope or parent nuclide. And then what you end up with as a result of the decay process is known as the daughter nuclide or daughter isotope. There are several different ways in which a radioactive substance may decay. We'll start off with beta decay. Beta decay, it's important to know, occurs to nuclei that are neutron rich. Sorry about that. Neutron rich. So sometimes atoms have too many neutrons, even though neutrons do act to stabilize the nucleus. So if you take a look again on page 936 in the textbook, figure 26.1, we see that if you have a substance that has a neutron to proton ratio that is too small, that substance may undergo beta decay. So beta decay or beta emission uh, involves the emission of a beta particle. Now, a beta particle is basically an electron, or it has the same properties as an electron. Now, hopefully you're thinking, wait a second, there's no electrons in the nucleus. How can the nucleus emit an electron? Well, this electron, and it's really not an electron, this beta particle is produced by something in the nucleus, either a proton or a neutron. I'll show you in a little bit. And it turns into a beta particle along with something else, and that beta particle is emitted, which means kind of spit out, kicked out of the nucleus. So when it says there consists of an electron, a better explanation would be it has the same properties as an electron. And by properties, I'm talking about mass and charge. So a beta particle has no mass, just like an electron, and has a charge of -1. Now, these beta particles are able to travel very fast, so they approach the speed of light, and consequently, they're somewhat dangerous to us. So we talk about the dangers of the different types of radiation, often in terms of penetrating ability, so what types of materials they can pass through. So beta particles can easily pass through a sheet of paper. What blocks beta particles would be a thin piece of, say, metal foil, like aluminum foil. Beta particles can definitely penetrate through our skin, get into our bodies, and cause all kinds of problems. So we'll compare relative penetrating abilities of the different types of radiation. Beta particles, pretty dangerous, pretty high penetrating ability. All right, symbol for a beta particle. So I will take one of two things. So again, think about like a nuclear symbol. And so the mass goes on top and the charge on the bottom. And so my favorites, or the one that I like to use for a beta particle, is this. That's kind of a weird looking beta. Let's try that again. That's still weird, but you get the idea. So it's a Greek letter, beta. It's not a B. Looks like a B. It's got that little tail there. So 0 over -1. So mass of 0, charge -1, beta. Or sometimes written like that. So either way is okay. I prefer Greek letter beta. In fact, there it is. We saw it right here. Sometimes, too, it's written as beta negative, because we'll see in a little bit that there's a positive beta as well. All right, let's take a look at some examples. Does anybody happen to know the radioactive isotope of carbon? Carbon has 3 naturally occurring isotopes. They are carbon 12, carbon 13, and carbon 14. If you guess carbon 14, you are correct. Carbon 14 will undergo beta decay. So let's do this. Let's write a nuclear equation showing this process. And so what's different about a nuclear equation compared to a chemical equation is that in a nuclear equation, we're going to use these symbols. And every symbol in the equation will include mass and charge. So let's start off with a nuclear symbol for carbon-14. So that's 14 over 6C. And it will undergo beta decay. Now, before we look at this equation, let's talk about where this comes from. Where does a beta particle come from? It comes from something in the nucleus that is turning into that. So keep in mind that substances that undergo beta decay have too many neutrons. And so it's a way of decreasing the number of neutrons without changing the mass, as we'll see. So let's write the equation showing this transformation where a neutron turns into a beta particle. So let's start off with the symbol for a neutron. A mass of 1, a charge of 0, N. And what happens is a neutron breaks apart into a proton, mass of 1, charge of 1, and a beta particle, mass of 0, charge of -1. So that leaves the nucleus, and the proton stays behind. So essentially, you're taking a neutron and you're turning it into a proton. So both a neutron and a proton have a mass of 1 AMU, about 1 AMU. And so when a nucleus undergoes beta decay, the mass does not change. Well, what happens to the charge? Be careful. A lot of students will mess this up. And if you know how a beta particle forms, your chances of messing this up are greatly decreased. So you take a neutron, you turn it into a proton. So when a substance undergoes beta decay, though the mass does not change, the charge does. The charge of that nucleus increases by 1. You're gaining a proton. All right, so let's do this. Let's start off with our beta particle. And when we write nuclear equations, we want to balance mass and charge. So what plus 0 is equal to 14? Well, our daughter nuclide, our daughter nucleus, has a mass of 14, just like our parent nuclide. And then what plus -1 equals 6? A lot of times I get that. And that is bad math. 5 plus -1 is not 6. So what plus -1 is 6? That, of course, would be 7. And then we go to the periodic table. What has a charge of +7? A nuclear charge of +7. What has 7 protons in its nucleus? That would be nitrogen. So what we say here is that carbon-14 transmutates. Oh, that's a fancy word for turns into. Transmutates into nitrogen-14. All right, here's another example. Cobalt-60 undergoes beta decay. So let's write the equation for that process. What is the nuclear charge of cobalt-60? So find that on your periodic table. Cobalt-60 has a nuclear charge of +27. On the right side, we'll put our beta particle and then balance mass and charge. So of course, there's no change in mass. Charge increases by 1. And what has a nuclear charge of +28? That would be nickel. So cobalt-60 transmutates to nickel-60. That is beta decay. Next up, we have positron emission or positron decay. I usually call it positron emission. There we can see that symbol for a positron, also known as positive beta emission, is again a beta particle, or sorry, a beta, Greek letter beta, this time with a plus sign. So take a look again on page 936. What is likely to undergo positron emission? This is something that has too few neutrons. So regular negative beta was too many neutrons. Positron emission is when something has too few neutrons, neutron poor. So what exactly is a beta particle? A beta particle consists of look at that name, positron. Why did I say beta? Positron. What does a positron consist of? Well, think about what that word means. Positive, tron, electron, positive electron. So again, really not a positive electron, but has the same properties as a positive electron, that being the same mass as an electron, so basically zero, but with a positive charge. Like beta radiation, positrons approach the speed of light, giving them rather high penetrating ability. All right, symbol for a positron. Again, there's a couple we can use. I prefer this one. So, whoops, let's scooch that in. It looks kind of weird. So, zero mass, positive one charge, beta, or 0 over negative 1. Whoops, that's positive 1. Sorry. 0 over positive 1 E. All right, so once again, hopefully you're thinking, wait a second. I thought the nucleus only contains protons and neutrons. Now you're saying that the nucleus contains electrons? No, not really. Or the nucleus contains positrons? No, not really. So just like a beta particle is produced by something in the nucleus, that something being a neutron, a beta particle is also produced by something in the nucleus. Well, if it's not a neutron, it must be a proton. So let's take a look at that first. Again, neutron-poor or proton-rich, right? We can put that there as well. Too many protons in the nucleus. So this is a way for the nucleus to get rid of a proton. So let's start off with a proton. That proton is going to break apart into a beta particle, and what's left? 1 over 0, mass of 1, charge of 0, that's a neutron. So beta decay, sorry, I keep saying that. Positron emission, you take a proton and turn that into a neutron, so again, this leaves. So the mass does not change, but this time what happens to the charge? You're taking a proton, turning it into a neutron, the charge will decrease by 1. So an example of that is aluminum 26 undergoes positron emission. So let's write that equation. What is the nuclear charge of aluminum 26? That would be 13. Positron emission, so we want to write the symbol for a positron, 0 over plus 1 beta, and then balance mass and charge. So we said that the mass does not change, but the charge is going to decrease by 1 this time. So what plus 1 is 13? That would be 12. What has a nuclear charge of plus 12? That would be magnesium. So aluminum 26 transmutates into magnesium 26 via positron emission. All right, next up we have electron capture. Electron capture will occur with nuclei that are neutron-poor. I think we just said that, didn't we? Interesting. So both of these happen, and you can see that in your table or the graph on page 936, that this occurs with nuclei that are neutron-poor or proton-rich. So what happens during electron capture? It's exactly as you think. The nucleus captures an electron. So it says occurs when an electron in the first principal energy level, so we're talking about the electrons closest to the nucleus, not a valence electron, that's way too far to get sucked into the nucleus. First principal energy level falls into the nucleus. Electrons in higher levels then cascade down to fill the orbitals, and you know what happens when electrons go from a higher energy level to a lower energy level. Energy is released in the form of light. Interestingly, No particles are emitted this time. So nothing is spit out of the nucleus. Well, what exactly happens? Let's take a look again. So any guesses what happens with that electron that's sucked into the nucleus? Remember, electrons are negatively charged. Maybe it's attracted to something that's positively charged. So we have this. Now this time we have no option. We don't want to put 0 over -1 beta because we're talking about a real actual electron. So the symbol is 0 over -1 e only. So proton combines with an electron to make what? So we get a mass of 1, 1 plus -1 is 0, charge is 0. What is that? Neutron. So once again, we see that a proton is being converted into a neutron. So mass does not change, charge will decrease by 1. All right, let's take a look at an example of a substance that undergoes electron capture. Let's go with aluminum 26. So aluminum 26 undergoes electron capture. What's the charge of nuclear charge of aluminum 26? That would be 13. If you're saying to yourselves, this looks familiar, it should. I'm going somewhere with this. All right, so this time we do have another substance as a reactant, so to speak, and that is our electron. So that's going to go on the left side with our parent nuclide. And like I said, it's not 0 over -1 beta. It has to be 0 over -1 e. Mass does not change. Charge decreases by 1. We end up with magnesium 26. So what do you notice? We end up with the same nucleus. So of course it's the same. So even though the processes occur differently, the results are the same. So positron emission and electron capture have the same effect on the nucleus, that being a decrease in charge by 1. All right, next up we have alpha decay or alpha radiation. I usually call it alpha decay. One symbol we can use for an alpha particle is this Greek letter alpha. Looks like a, I don't know, a little fish. I kind of draw it like this. Whoops, that is a bad one. It's been a while since I've drawn that symbol. So that's a Greek letter alpha. There's another symbol that we're going to use as well. So what does alpha decay occur to? Take a look on page 936 and see what it says. Alpha decay occurs to heavy nuclei, a heavy nucleus that is neutron-poor. So it's, again, a way for the nucleus to get rid of some neutrons. The alpha particle that's emitted consists of a particle that has a mass of what? Well, it says consists of 2 protons and 2 neutrons. So what is the mass of an alpha particle? Each proton and neutron having a mass of about 1 AMU. So an alpha particle has a mass of 4 AMU. What is the charge? Well, 2 protons, 2 neutrons. Protons are positively charged, neutrons no charge. Charge of 2. So it's a particle that has a mass of 4 and a charge of 2. Again, we'll get to the symbol in just a second. These are rather slow moving, 0.1 the speed of light, so that's 30 million meters per second instead of 300 million meters per second. Still pretty fast, but relatively speaking, slow. Consequently, alpha particles have the lowest penetrating ability. Remember I said that beta particles can easily pass through a sheet of paper, and to block beta particles you need thin piece of metal, something that's pretty dense and prevents those particles from passing through. Alpha particles can pass through a single sheet of paper, cannot pass through even a single sheet of paper. So can alpha particles, you think, pass through our skin and get into our bodies? Nope. Nevertheless, alpha radiation is very dangerous, especially if you are consuming foods or drinks that have this type of radiation, or substances that give off this type of radiation. So that's how often alpha particles can get into our bodies, through ingestion. Anyways, symbol for an alpha particle, we got a mass of 4 and a charge of 2. Anything else that you know of that has a charge of +2? Go to your periodic table and see. Now, something to keep in mind. When something undergoes alpha decay, it does not emit a helium atom. This is not a helium atom. An alpha particle has the same composition as a helium nucleus. There are no electrons here. So I don't really like the use of He there, because people think it's helium that's being given off. No, it's a particle that just consists of 2 neutrons, 2 protons, just like a helium nucleus. All right, let's take a look at some examples of substances that undergo alpha decay. All right, we'll do a couple of these. One of them is uranium-238. Uranium-238 is radioactive, has more than 82 protons, so all of its isotopes are radioactive, and it will undergo alpha decay. So let's start off with the symbol for uranium-238. So mass of 238. What is the charge of a uranium nucleus? That would be +92. Symbol is U. So start off with our alpha particle, and then to figure out the daughter nuclide, balance mass and charge. So the daughter nucleus has a mass of 234 and a charge of 90. What has a nuclear charge of +90? That would be thorium. So uranium-238 transmutates into thorium-234. So notice alpha decay results in a change in both the charge and the mass. Mass decreases by 4, charge decreases by 2. Here's another one. A different isotope of thorium-232 undergoes alpha decay. Thorium-234, interestingly enough, undergoes beta decay. Like uranium, thorium has no stable isotopes. This one also undergoes alpha decay. And so the nucleus we end up with has a mass of 228 and a charge of 88. What has a nuclear charge of +88? That would be radium. Have you seen Radium Girls? About the clock makers, watchmakers? Radium is radioactive. Unfortunately, not everyone realized the effects of that radiation. All right, one more type of radioactive decay is known as gamma radiation or gamma emission. Gamma rays consist of high energy waves. So it's a form of electromagnetic radiation, like ultraviolet lights and visible lights. We have gamma rays or gamma radiation. Gamma rays, because they're a form of electromagnetic radiation, have no mass and no charge. So they don't result in a change in the composition of the nucleus like the other decay processes do. Gamma rays travel at the speed of light and have an extremely high penetrating ability. Now, you know how dangerous X-rays are to us. Gamma rays, even more energetic, even more dangerous. So because gamma rays have no mass and no charge, they don't appear, we usually don't write them in nuclear equations. If we do, again, the nucleus, daughter nucleus that you end up with has the same composition, but has a less energy. So it's a way for the nucleus to release excess energy. In fact, gamma radiation often accompanies the other types of decay processes. Now, it should be noted that many of the trans-uranium elements, so these are things that are after uranium on the periodic table, undergo spontaneous fission. That word fission refers to a splitting of the nucleus. So they can undergo spontaneous fission. We'll see later on examples of non-spontaneous fission. Spontaneous fission where the nucleus splits into two isotopes of approximately the same mass. And when this happens, excess neutrons are emitted. And when this happens, gamma rays are also emitted. All right, let's take a look at some examples of radioactive decay in nuclear equations. Example 26.3 and 942. It says write the balance equation for each of the following radioactive decay processes. Letter A, titanium-45 decays by positron emission. So we'll just go one at a time through these. So again, just like we said, we start off with titanium-45. Titanium nucleus has a charge of plus 22. Put a positron on the right side of the equation, balance mass and charge, and what we end up with is scandium-45. So again, positron emission results in no change in mass and a decrease in the charge by 1. So 21 plus 21, that is scandium. Krypton-81 decays by electron capture. So this one we show Krypton-81, 81 over 36. The electron that's being captured is shown as a reactant. And this results in, again, the mass not changing and the charge, again, decreasing by 1. So 1 less proton than krypton is bromine. So we end up with bromine-81. Letter C. Next up, we have ruthenium-105 decaying by beta emission or beta decay. So 105 over 44, we have a beta particle on the right side. This time the charge will increase by 1, so we go from 44 to 45, and so we're going to make rhodium of the same mass, rhodium 104. Lastly, radium-223 undergoes alpha decay. So start off with that, 223 over 88. Put an alpha particle on the right side, 4 over 2. Your book uses alpha. You can do 4 over 2 He. Mass decreases by 4, so we get 219. Charge decreases by 2, we get 86. All right, so go ahead and turn to page 965 and work on exercise number 35. And let's go ahead and do all three of those, A, B, and C. Fill in the missing piece, balance, mass, and charge, and see what we're missing. Pause now. All right, here's what we get. We got, obviously, they're very different equations than what we were working with. These are not all radioactive decay, but still we can figure out what's missing by just balancing mass and charge. So if you were to take a magnesium nucleus and bombard it with a proton, you would make an aluminum nucleus, and 1 neutron is emitted during that process. It's kind of hard to see the charges of the nuclei there. And then letter B, if we take aluminum 28, and bombard it with, that's a different symbol for a proton, 1 over 1H is just a proton, we get silicon 29 and a gamma ray, some gamma radiation. So 0 over 0, gamma is a symbol for a gamma ray. 12 over 6C fills in the missing blank for letter C, and 4 over 2 He fills in the blank for letter D. All right, lastly for this section is decay series. If we go to 947, this shows an example of one of the natural decay series. And what a decay series shows is all the steps in the decay of a substance. So this one shows starting off with uranium-238. It will decay via alpha decay to form thorium-234, which is also radioactive. It will undergo beta decay to form something else, and then another beta decay to form something else. That will undergo alpha to form something. That will undergo alpha. And so you have this long chain of events, one decay process after another, until you end up with something stable. So in the case of uranium-238, the stable nucleus that you end up with is lead-206. Go to 948. There are actually 3 natural, I can't speak today, 3 natural decay series. They are starting with parent nuclides uranium-238, which we just saw, uranium-235 and thorium-232. So you can think of it this way. All of the radioactive substances on Earth once started as either uranium-238, uranium-235, or thorium-232. We can see the rate of decay there as well, known as half-life. We'll talk about that in our next lesson. And just be familiar with these 3 decay series. All right, that concludes this lesson. Thanks for watching.